Good afternoon, everybody. This is Diptosri again, the coordinator of PICS Today webinar series. It's my great pleasure to welcome you all in our third webinar. And I would like to extend my special warm welcome to Dr. Gunther Rockens. He's a professor in Ghent University, Belgium. He'll give a talk on microtransfer printing of photonic circuits. Before having this interesting topic, I would like to request Professor Krishna Das to introduce our speaker. I'll also request our newly joined Professor Sudarshan to moderate our Q&A session. Over to Professor Das.
Yeah, thank you, Diptosri. Welcome you all and welcome our honorable guest, Professor Gunther Rockens. So I just need to give a little bit of introduction because he does not need any introduction. He is already very, very well known for his work on 3-5 integration and for silicon photonics. Particularly, you know that silicon photonics is having some bottleneck. It is an indirect bandgap semiconductor. It's very, very difficult to, it's not at all possible to monolithically integrate laser. So the alternative technologies are coming out. One of the very promising technology that is invented by Professor Rockens, and he will be talking about that today. I think we will be learning a lot from his interesting talk. And about himself, I think he actually born and brought up in Ghent University. He is engineering degree from Ghent University, PhD also Ghent University, and then joined as a faculty. Currently, he is a full professor. And in the meantime, in 2008, he was visiting scientist in IBM, IBM T.J. Watson Research Center, New York, and fully dedicated for silicon photonics, particularly 3-5 heterogeneous integration for the sake of silicon photonics. And he was the holder of European Research Commission starting grant, Miracle, to start up his research career in the field of integrated mid-infrared photonic integrated circuits. And since then, he is now is a pioneer figure for its silicon photonics and heterogeneous integration. So with this, I invite Professor Rockens for his talk. I hope everyone will be enjoying. In the panel, we have Dr. Sudarshanan and Soni, Dinanath Soniji. He is the Executive Director of SI2 Microsystems. And they will be also interacting during Q&A session. You can actually put up your question in the Q&A bar. Q&A icon is there, so there you put up your questions. I think as many questions as you can just put up. We'll try to make it answerable, and I think Gunther will try his best to answer that thing so that this webinar is become more attractive. With this, over to you, Professor Rockens.
Okay, thank you for the nice introduction. Let me see, can you see the slides?
Yes.
Okay, very good. Okay, so I'm, let me see, wait, just there's something popping up here. Yeah, okay. So I'm gonna give a presentation on the work my group is doing on microtransfer printing for silicon photonics. So let me start by posing the problem. So silicon photonics is a field that is rapidly evolving. Several platforms are emerging worldwide, including IMEX silicon photonics platform, which comprises a wide range of passive optical functions like filters, low-loss waveguides, coupling structures for fiber interfacing, but also high-speed optoelectronic components such as modulators in different flavors and photodetectors. But as was already mentioned in the introduction, what is missing on this kind of platform is a means to integrate optical amplifiers and light sources, lasers in particularly. And for this, we need 3.5 semiconductors. So we need to have a way to, in a scalable way, integrate 3.5 semiconductor devices onto such a silicon photonics platform. Now, next to the silicon waveguides platform, there is, of course, also other group 4 photonic platforms, such as silicon nitride waveguide circuits. And these circuits, they are purely passive today. So here you don't even have high-speed modulators or photodiodes monolithically integrated. Yes?
Sorry to interrupt. I think your display is swapped to the presenter's display.
Okay. Sorry about that.
No problem.
Let me see if I can change that.
I see something called swap displays in the top left.
Is this okay?
Yeah, that's perfect.
All right.
Thank you.
Sorry about that. So yeah, so besides the silicon platform, there's also silicon nitride, which is actually a purely passive platform today. So here you need integrate other materials both for light generation but also for modulation and detection. And since this nitride platform has a very broad wavelength range of operation, typically you want to have such components ranging from the visible to the shortwave infrared wavelength range. So again, here 3.5 semiconductor integration will be of key importance. Now, there are many methods to integrate 3.5 semiconductor devices on a silicon photonic IC, ranging from the pick and place of packaged lasers. So, for example, Cisco is commercializing this approach where you have a micro-packaged laser and you actively align it to an underlying silicon circuit. You could do flip chip integration of bare 3.5 dies. This is, for example, something that Rockley Photonics is commercializing. Or, as most of you probably know, there's also the die-to-wafer bonding approach, which is currently being commercialized by Intel. Now, what we are looking at in the group is basically, what's next in terms of heterogeneous integration of 3.5s on silicon. And so we are looking at two technologies. One is microtransfer printing, and the other one is heteroepitaxial growth. So today I will only be talking about microtransfer printing as an enabling technology. Now, you may ask yourself the question: why do we need yet another integration technique? Well, that is because we do still see quite some issues with the established approaches. Every approach has its pros and cons, and I try to list them here. I won't go through the whole list here, of course. Now, what is good about, let's say, the more classical hybrid integration approaches, such as the micro-packaged laser and flip chip integration, is that you have this known good die concept. You can test your 3.5 component up front and then integrate it on your silicon photonics target wafer. And that will then result in a higher compound yield of the photonic IC. Now, a die-to-wafer bonding approach does not have this known good die concept. So you only know whether the integration was successful after you have fabricated the entire chip and characterized the laser. So this kind of die-to-wafer bonding approach can result in a lower compound yield. On the other hand, there are also drawbacks to these techniques. On one hand, there is the for the hybrid approaches, the fact that it is a sequential integration process. You have to either actively or passively align the 3.5 component to the silicon and then put it in place. So this means this is a low throughput integration process. That's an advantage of the die-to-wafer bonding approach, because here you have the parallel processing of the devices, so the throughput is higher. Now, we believe that microtransfer printing is a technology that combines advantages of these hybrid integration approaches with the advantages of the die-to-wafer bonding approach. So let me first explain to you what microtransfer printing is. I'll do this by this cartoon, where on the left-hand side you see our 3.5 source wafer. On that 3.5 source wafer, we have already processed the 3.5 optoelectronic components that we want to integrate on the silicon photonics target wafer. So that means that after processing of the 3.5, we can actually test these components and basically select the known good dyes from this wafer. So that's what it has in common with flip chip integration, is that you can fabricate the 3.5 devices on a 3.5 source wafer and test them up front. So you have this known good dye concept. But then, in order to integrate these components onto the silicon photonics target wafer, we are not picking up and aligning one component at a time. We are picking up arrays of components at one time. So here now, for clarity, I just drew 4 devices that are picked and printed in one operation, but this can scale to several hundreds or thousands of devices. So this way, you also inherit the high throughput integration that, for example, technologies such as die-to-wafer bonding provides you. So here I listed some of the advantages that I see in the technology. As I said, it's 3.5 processing on the source on the 3.5 wafer and testing prior to integration. It's a back-end integration technology, as I will show you later on. We don't have to change anything to the silicon photonics process flow. It's high throughput integration because of the fact that we can transfer print large arrays of components. As you will see later on, we can also get efficient optical coupling between the 3.5 and the silicon because of the use of adiabatic taper structures. One thing that is still, not yet there is the supply chain. So we need to build the entire supply chain from 3.5 foundries offering transfer print ready components to an OSAT or an assembly house that does the microtransfer printing to the post-processing on the silicon photonics target wafer. Now, how does this microtransfer printing process work? Well, if you look at the 3.5 source wafer, it's not so different from the classical 3.5 device fabrication. So what you start with is a 3.5 layer stack. So substrate and then an epitaxial layer stack. The only thing you need to do to enable the transfer printing is to include a release layer, a sacrificial layer in the 3.5 layer stack. So what you do next is you pattern your 3.5 device. You also pattern the release layer, and then you encapsulate it with a dielectric material. And that dielectric material is designed such that on one hand, it anchors the patterned device to the substrate through these so-called tethers here. But there are also openings in that encapsulation layer such that you can selectively etch away the release layer here, such that you're left with the thin film devices here attached to the substrate by these tethers. So now you can come in with your stamp, and that stamp you will laminate the device to the stamp and pick it up, thereby breaking the tether. And similarly on the target wafer, you then print the device on the silicon target wafer. Now again, here this picture shows a single device that's being picked up and printed, but this is a process that can be done massively parallel. So here you see an example of 3.5 components that are ready to be transfer printed. So this is a microscope picture from the 3.5 source wafer. So what do we see on the left-hand side? This is, for example, for a photodiode. You see a very simple PIN mesostructure here. These dark structures here, those are the tethers. In this case, this is implemented using photoresist. And this colorful layer here is the sacrificial layer that is being etched. So this is during the etching of the sacrificial layer. So after the sacrificial layer etching is finished, you get freestanding PIN photodiode structures here on a 3.5 substrate. And similarly for waveguide type components, such as semiconductor optical amplifiers, you can do something similar. You have the 3.5 device, you have the tether structures here, and you have the release layer that is to be etched. Now, the stamp that is used to pick up and print these components is made out of PDMS. PDMS has several advantages for this application. First of all, it is transparent, and as you will see later on, we will use this for the alignment process. Secondly, you can cast PDMS on a master and then basically make structured stamps. So you can, in the PDMS, create an array of posts on a particular pitch for your application, which allows you to pick up a subset of 3.5 components from the 3.5 source wafer and print it to the target wafer. Now, these stamps, they are quite robust. So over 30,000 print cycles with a single stamp have been demonstrated. Now, how does the pickup and the printing process work? Well, the basic idea is that we exploit the viscoelastic properties of PDMS. And that means that if you laminate PDMS against the material, the adhesion between the PDMS and the material will depend on how fast you peel off the PDMS from the material. The faster you peel it off, the stronger the adhesion is between the stamp and the device. So this is shown here in this graph, where we plot the adhesion between the device and the stamp as a function of the peeling rate. So what is now the idea? The idea is that you design your tether structures such that the force or the adhesion between the stamp and the device is stronger than the tethers during the pickup process. So that in that case, the device remains attached to the stamp and you break the tethers. While in the case of the printing, you actually use a very low peeling rate, such that the adhesion between the stamp and the device is weak, such that the device remains attached to the silicon target wafer. So by optimizing that, you can get a high yield pickup and printing process. So this is then how it looks like. So this is a picture of such a stamp on a glass plate. You see that you can make these structured posts on it to pick up a subset of devices. This PDMS is compliant. That means you can overdrive the stamp onto your source and target wafer to get an intimate contact between the two. The PDMS sits on a glass plate. That means that it's a laterally stiff structure. So that means that the pitch of the devices on the source remains intact after transfer printing on the target wafer. It's a soft material, so you don't have to worry about damaging fragile components. And as I said, it's transparent, which means that after picking up, you can basically, like in a mask aligner, align your coupons, your 3.5 devices, to the target wafer and do the printing. So the process is actually very simple. You have a chuck with a source wafer, a target wafer, and this square, rectangular square here is actually a cleaning pad. So after each printing cycle, you go to this cleaning pad to clean the stamp. You pick up an array of devices, you print it, and then you clean the stamp. So today's tools that you can buy on the open market are actually quite good in terms of alignment accuracy and throughput. Now, current tools, they have an alignment accuracy of about 0.5 micron 3 sigma. When you are printing medium-sized arrays, and medium size is, well, it's not so small for photonic applications. It's already about 1 inch by 1 inch. So that's more or less one reticle of the silicon photonics wafer that you can print in one operation. And one print cycle takes about 60 seconds. And in that one print cycle, you can populate the entire single reticle with 3.5 components with an alignment accuracy of 0.5 micron. So this shows that this can indeed be a high throughput process. Now, how do we envisage the integration on, for example, an advanced silicon photonics platform? Is we just take the silicon photonics wafer out of the line after the backend has been completed. So we don't change anything to the silicon photonics process flow. What we do then is we define a recess, a cavity in the backend, using classical litho and etch processes. We apply a very thin adhesive bonding layer, BCB in this case, and then we print the thin film 3.5 components, for example, indium phosphide PIN structure. Inside that recess, we cure the adhesive, and then we do a backend metallization that connects the 3.5 contacts to the backend of the silicon photonics wafer. So in terms of number of processing steps to integrate the 3.5, it's actually very moderate. Now, how do we optically couple between the 3.5 and the silicon? Well, that depends a little bit on the exact device that you are interested in integrating. For most of the waveguide type devices, such as optical amplifiers or modulators or lasers, we typically use an evanescent coupling scheme where we have a 3.5 waveguide here sitting on a silicon waveguide layer, and by tapering down the 3.5 waveguide layer, we basically squeeze out the light from the 3.5 into the silicon, as is shown here, or vice versa. We can also go from the silicon into the 3.5. So the good thing about this kind of taper approach is that it is robust against misalignment, as you can see here. If we make the taper long enough, we can even support 1 micron of misalignment. And remember that the state of the art has 0.5 micron of alignment accuracy. Plus, it's a very broadband interface and low back reflection interface. Now, this is for coupling between 3.5 and silicon. As said, we also want to integrate these 3.5 devices on silicon nitride waveguide circuits. Well, for that silicon nitride integration, we actually make use of an intermediate silicon layer. So we have silicon nitride at the bottom, then we have a silicon intermediate layer, and then we have the 3.5 on top. So it's basically becomes a two-step taper structure to couple light from the 3.5 into the silicon nitride. Now, for some other types of components, we are not using evanescent coupling, but we are using gratings. So here you see an example of a VCSEL, a vertical cavity surface emitting laser, that emits its light perpendicular to the photonic IC, which we then, using a diffraction grating, couple into the silicon nitride layer. And here you see something similar for a photodiode integrated on top of a grating coupler. So I'll come back to these devices later on. Now let's talk a bit about the use of the 3.5 material. So here you see a schematic of a 3-inch wafer on which you can fabricate your 3.5 source devices. Now, if you assume that we are using a 1-inch by 1-inch stamp, that means actually that effectively we can use this pink square of the 3.5 wafer to pick up and print components from a 3.5 source wafer to silicon target wafer. So if you do the calculation, that leads only to a wafer usage of about half, about 55% in this case. Assuming, of course, you take the biggest possible stamp of 1 inch by 1 inch. However, if you look at the devices themselves are extremely small. Typically, you can put these devices like a waveguide-based amplifier, you can put them on a pitch of about 70 micron on the 3.5 source wafer, in one dimension, of course, here. In the case of a square device, like a photodiode, you can put them on a 70 micron pitch, both in the X and the Y direction. So that means if you compare that to a classical flip chip type device, yeah, these pitches there are typically a factor of 3 or 4 higher. So we're talking about dies of 200 micron to 300 micron in width. So this means that even though you only use 55% of the wafer, your packing density of components is a factor of between 3 in the case of an elongated device, but up to 10 in the case of a square device, larger, such that you make more efficient use of the 3.5 source material. Now, in our group, we are mostly working on 3 material systems: indium phosphide, gallium arsenide, and gallium antimony, to develop these microtransfer printing processes. So in our group, we are following a two-pronged approach. First of all, we do process development ourselves to develop the processing of the 3.5 devices, the release, and the printing. But then we also work with 3.5 foundries to take up these processes and establish a supply chain. So this is currently carried out in the context of 3 European projects, one using Smart Photonics as a 3.5 foundry, where we are printing indium phosphide C-band devices. One where 3.5 Lab is the 3.5 foundry, where we are also printing indium phosphide devices in the 1400 to 1700 nanometer wavelength range. And one project where we work with Inolume as a 3.5 foundry to transfer print gallium arsenide quantum dot SOAs or lasers on silicon photonics. So now let me give you an overview of the type of devices we have been working on in the recent past. We have the most experience with indium phosphide-based devices, so the largest number of results have been obtained so far, but for indium phosphide. But I'll also elaborate a bit on gallium arsenide and gallium antimony. So for indium phosphide on silicon devices, the first thing we did is demonstrate an SOA, so where we transfer print an indium phosphide PIN waveguide structure on top of a silicon waveguide structure. And in this experiment, we actually made two designs. One where the light is completely transferred from the silicon into the III-V. So in this case, the mode is completely confined in the III-V in the gain section. Or a second structure where, as shown here, the mode is only partially transferred from the silicon to the III-V. So clearly, this top structure here will have a larger gain because the overlap between the modes and the quantum wells is higher in this case. However, the case of the partial transfer is also interesting because then you get a higher output saturation power. Moreover, the fact that you have this silicon below implies that your coupling structure here becomes more alignment tolerant. So it means that for most of our current research, we are focusing on this kind of III-V on silicon active cross-section, so where the light is partially in the III-V and partially in the silicon. Okay, so based on this technology, then we demonstrated the first widely tunable lasers using microtransfer printing. So here you see a schematic of the laser. Sorry, so you have silicon filters that form the laser cavity. You transfer print III-V SOAs on top, and then you post-process the metallization. So that was done in 2019, where we showed, say, normal kind of behavior for these kind of devices. So tuning range of about 50 nanometer, good SIMO suppression ratio, and a few milliwatts of optical output power. So since then, we have worked further on this technique. So, well, here in this case, we started off with a simple passive circuit. We printed the SOAs, and then we did post-processing of the heaters. Now, this post-processing of the heaters is actually something you would like to avoid, and you would like to do that before you integrate the III-V SOAs. So that's illustrated here, where actually now we are processing the silicon and the heaters up front. We're then etching cavities in the back end, and we are printing the III-V component in that cavity. So using that approach, we recently integrated two different III-V gain, two different III-V SOAs on the same photonic IC right next to each other, one with a gain peak at 1525 and one with a gain peak at 1575. And this way together we could cover a tuning range of about 125 nanometers. So this also shows you the strength of microtransfer printing is that you can very intimately integrate different III-V components on a single photonic integrated circuit. Now, the next step then was to integrate on IMEC IC50G platform. I've already shown you this cross-section here. This is how the amplifier cross-section looks like. So it's similar as before. The mode is partially in the silicon and partially in the III-V. And I've also shown you here how we can transfer print inside recesses on the silicon photonics backend. So this then resulted in the first SOAs integrated on an IC50G silicon photonics circuit. So that comprises high-speed modulators, high-speed detectors, switches, and the passives. So these SOAs currently have about a gain of about 10 dB for close to 100 milliamp drive current. Now, using this technology, then we did also the first widely tunable lasers on this platform. So you recognize here again the ring resonators that we use to form the laser cavity. And here in this recess, we actually printed the 3.5 SOA here. So this is before this picture is taken before the final metallization, such that you can clearly see the 3.5 coupon. And on this platform, of course, we have also the high-speed modulators as shown here. So this again resulted in a C-band tunable laser. But in this case, connected to a high-speed modulator as a proof of principles. This will be presented at OFC later this year. So something similar was then done on silicon nitride waveguides, as I said, using an amorphous silicon interlayer. So we have a two-layer taper, which first transitions, let's look at it from this side, from the 3.5 on silicon mode to an amorphous silicon waveguide mode, and then into the silicon nitride. So here we also got similar performance, about 10 dB of gain for 100 milliamps of drive current. Using this technique, then we built mode-locked lasers. In this particular project, the idea was to make very low repetition rates mode-locked lasers, so below 1 gigahertz repetition rate for microwave photonics applications. And in order to realize such a low repetition rate, you need very long cavities. And here we exploit the very low losses in silicon nitride to form these low loss cavities. So this was a first example of a sub 1 gigahertz 3.5 on silicon nitride block laser. Some very recent results that will be presented at CLIO later this year is the transfer printing of UTC photodiodes, so high-speed 3.5 photodiodes on silicon nitride waveguide circuits, where we get over 100 gigahertz of bandwidth and a reasonable responsivity in the C-band. So this kind of technology is now being developed further, as mentioned before already, in the context of a European project called INSPIRE, where the idea is to work with a 3.5 foundry to provide the C-band active devices, the SOAs, modulators, and detectors, and to transfer print these massively parallel on a 200 millimeter silicon nitride waveguide wafer. So now let's have a look at gallium arsenide-based devices. So I already showed you this picture of the VCSEL, so gallium arsenide 850 nanometer VCSEL. That was transfer printed on top of a silicon nitride waveguide circuit. In this case, it's PECVD silicon nitride, where we use the grating to couple lights into the silicon nitride, but actually we also use it as a way to pin the polarization of the VCSEL. This is a one-dimensional grating, which will have a different reflection coefficient for TE and TM polarized light. And by optimizing that, by choosing the proper spacing between the VCSEL and the silicon nitride, we can create substantial difference in threshold gain for TE and TM polarized lights, and hence bend the polarization of the device. So here you see the VCSELs on the 3.5 source wafer. So again, a very dense array. In this case, we picked up individual VCSELs and printed them on the silicon nitride grating coupler here, resulting in low threshold lasers, sub half a milliamp, single polarization, and single wavelength emission devices here. So this kind of VCSELs could be used, well, for example, they could in principle be used for optical interconnects, but at the moment the output power levels are still too low for such an application. But it is, for example, a very well suited component because it's single mode and it tunes in a mode-free way. For example, to interrogate a refractive index biosensor implemented on the silicon nitride platform. So similarly, we also printed gallium arsenide photodiodes for 850 nanometer operation. In this case, it shows the array printing of these photodiodes. Yeah, here we don't have the best quantum efficiency at the moment. It's less than 50%. But here the idea was mostly to demonstrate the concept, microtransfer printing, short near-infrared photodiodes on silicon nitride waveguide circuits. Now, in an other European project, Caladan, we are now trying to scale up this gallium arsenide transfer printing. For, on one hand, the integration of gallium arsenide quantum dot lasers on silicon photonics. But on the other hand, also we're also working on the transfer printing of electronics on silicon photonics wafers. So as for the lasers, this is still work in progress. So we have now all the building blocks to realize O-band tunable lasers on silicon photonics. This is done on a 300 millimeter silicon photonics platform. So we can pattern these first order gratings using immersion lithography on 300 millimeter silicon wafer. And now we are working on developing the gallium arsenide process and the release process to transfer print these components. So that's work in progress at the moment. And then finally, we are also looking at gallium antimony devices. This is still lowest TRL at the moment. But what is the idea? The idea is that we can, using gallium antimony based materials, you can also address the 2 micrometer wavelength range. And the 2 micrometer wavelength range is interesting for spectroscopic sensing applications. Many biomolecules, for example, have characteristic absorption features in the 2 micrometer wavelength range. So for this, we also want to be able to transfer print gallium antimony SOAs onto a silicon photonics platform. And in principle, we can also combine it then with indium phosphide and perhaps even gallium arsenide SOAs on the same chip. So this is work under development. So for the optical coupling, we need actually silicon germanium waveguides instead of silicon waveguides because of the higher index of the germanium. And we also need, of course, to be able to transfer print gallium antimony. So this is under development. So at the moment, we have germanium waveguides with reasonable losses, about 4 dB per centimeter. And we also were able to demonstrate the first transfer printing of gallium antimony, in this case still dummy coupons in such a recess on a silicon photonic stamp. So that was the 3.5 activities. Then I just in two slides I want to summarize to show that this microtransfer printing is actually a very versatile technology. Every material or device that you can release from a substrate in principle can be transfer printed. So you see some examples here of other things we do. So transfer printing of lithium niobate on silicon nitride waveguides. But as mentioned before, also transfer printing of electronic chiplets on silicon photonics. Silicon active components fabricated on an SOI platform. We can transfer print, for example, silicon nitride. And some early work, as you can see from the picture, is trying to transfer print magneto-optic materials from a source wafer to a silicon photonics target wafer to build integrated optical isolators. So with this, I would like to conclude, and I'm happy to answer any questions you might have.
Thank you, Gunther. Very nice talk. It's very nice to see some of the work on gallium antimonide, and also some of the last few slides were a good teaser, I think, for a lot of people. I just wanted to remind people to just put in their questions in the Q&A box and not the chat box. So let me go through some of the questions before I have a few of my own. So Yash asks, in the process flow, how do we make sure that the support breaks symmetrically?
The question that the support breaks symmetrically, is that?
Yeah, I think that's what he has written.
Not sure I fully understand, but for example, if you look at this plot here, for the pickup process, the stamp is only moving up and down. There is no lateral movement of the stamp, so we don't see any issues with having the tethers break differently on the left-hand side or on the right-hand side.
I guess I can probably ask a slightly different question. Do you perhaps have cases where you have the bottom surface not being planar, like during the break, like having something that's in the Z direction, like some tether protruding in the bottom?
Yes, yeah, that's a good question indeed. So if you would have tethers protruding below your, below the bottom of your device, then you have a problem, of course, because then you cannot print the component on the target wafer. So that's why in this drawing, as you can see, we have these horizontal tether structures, and we make sure that the weakest point of the tether is in this horizontal plane, such that it always breaks in this horizontal plane. And then you don't have this issue with tethers that protrude below your device.
Yeah, I hope that answers Yash's question, perhaps. Then Sharad asks why there are some grooves on the silicon substrate below the printed device. I guess that's the waveguide definition. I'm assuming the rib.
Grooves? Not sure.
Yeah, I think he's probably referring to the rib edge that defines the waveguide. So I guess that's just necessary to define the waveguide.
Yeah. Indeed. So, but in the end, well, perhaps I can show the schematic cross section here. So in the end, you have something like this. So you have a planar surface onto which you print.
Right.
But of course, in that planar surface, you have a rib silicon waveguide or a strip silicon waveguide to guide the light. Yeah.
Right. Okay, next question is from Ashutosh. How is the alignment between the 3.5 and silicon chip done while printing?
Mm-hmm. So that is shown. Let me see.
It's a see-through stamp, right? So you can
It's
use the
indeed
camera.
it's a see-through stamp. So you're looking from the top with a camera to the coupons that you've picked up on the stamp. You see the target wafer, and then it just uses a pattern recognition algorithm to optimally align the two, and then you go into contact.
Okay.
It's really like it's really behaving like a mask aligner at that step.
May I just add to what Professor Gunther said was that I've been talking to Ashutosh and all these guys on the packaging side. The pattern recognition markers is what we use on the chip as well, right, for wire bonding.
Mm-hmm.
And for all the machines are use optical alignment systems, and so we from the markers, the pattern recognition markers, we know what the fiducials are and where we go and place that. So that is what is used over here, and that's exactly what I suppose IMEC is also doing.
Yes, indeed. So if you see, for example, here, for example, on these coupons, we have some alignment markers here, and then there are complementary markers on the silicon. And the pattern recognition software recognizes these markers. It draws a box around it. It finds the center. It does the same for the outer markers, and then it aligns center to center, the coupon to the target. Yeah.
Cool. Thank you. So then the next question is from Ram Mohan. How will you handle the temperature created by the laser diode affecting the optical properties of silicon photonic devices?
Okay, but it's a bit of indeed a common problem in 3.5 on silicon devices. It doesn't really matter which integration technology. That is that you have your 3.5 device, for example, a VCSEL, but it can be any device that generates heat. And of course, you need to sink that heat, and one way is to do it through the substrate. But here you have this thick buried oxide layer that prevents an efficient heat sinking. So there are several ways to overcome this. Currently, we are looking into the use of basically flip chip integration. So after we have realized our 3.5 on silicon PIC, we will flip it upside down on a heat spreader, like an aluminum nitride heat spreader, to basically sink the heat from the top instead of from the bottom. So that's one way. But then we are also looking into other ways by providing basically extra thermal vias through the oxide layers here. For example, you can imagine if you would have metal plugs here that connect the 3.5 layer thermally to the silicon. That also substantially reduces the thermal impedance of the device. So those are the two approaches we are looking into at the moment to enhance the thermal impedance. And according to simulations, it should lead to a factor of 2 to 3 improvements in thermal impedance compared to this kind of configurations.
Interesting. Okay. Next question is from Kumar Piyush. As LiDAR is an emerging technology, how much the VCSEL integration with silicon or silicon nitride will be useful for LiDAR?
Well, I don't immediately see this being used for LiDAR. The output powers are too low at the moment. These are not the classical high power VCSEL arrays that we are targeting here. We are targeting actually very low power consumption light sources on silicon photonics. So I don't immediately see that being used for LiDAR, but then it would rather be the waveguide coupled C-band SOAs that would be useful to build, for example, an FMCW LiDAR system on a chip. We are currently working on improving the output saturation power of these SOAs up to the 50 milliwatts level. And of course, also the story of heat sinking there becomes important.
Yeah. Right. Next question is Suvarna. She asks, is microtransfer printing better than heteroepitaxial growth? I don't know in what sense, but there can be different.
Yeah, indeed. It's as I said, there are pros and cons to every technology. I think heteroepitaxial growth is still very early days, especially in the context of heteroepitaxial growth for integration of 3.5s on a silicon photonics platform. I think in terms of standalone devices, there's already a lot of progress being made, but how to combine that now with an advanced silicon photonics platform, there's still a lot of questions to be answered. So yeah, I think it's just an evolutionary thing. Step by step, you are increasing the density of integration and the throughput. And I think microtransfer printing should be able to already go a very long way in enabling that, and only for perhaps the most advanced, the highest density circuits, which perhaps we cannot yet imagine, heteroepitaxial growth would be required.
All right. We have a question from Ranovus, George Roel. Thank you for the great presentation. Could you please comment on the thermal impedance of transfer printed components on top of the buried oxide for lasers and SOAs?
Yeah. So yeah, as I said, I already partially answered that. So
I guess you could compare it to traditional BCB-based bonded die-to-wafer bonded impedance.
Okay, yeah, there is no difference.
Okay.
I mean, it doesn't matter. I'm just looking for a cross section. Yeah, for example, here, it doesn't matter. Well, if you look at this cross section, it could as well have been a die-to-wafer bonded device. The device looks exactly the same after the integration. So the issues with thermal impedance are exactly the same. So as I said, yeah, we are exploring two routes. One is flip chip, one is with thermal vias through the box to substantially reduce that thermal impedance.
Right, and there have been several papers also, George, both from I think whoever is working on heterogeneous integration, they've hit on this thermal impedance problem. So I'm sure you can find literature if you want the exact like Kelvin per watt kind of numbers.
Sure. Yeah.
So Pratyasha asks, what is the typical footprint of a PIC after the integration of active devices, and how does it compare with respect to an equivalent electronic IC? I don't know if it's a fair comparison, but I guess you can talk about footprint, I guess.
Yeah. So, well, of course, it really depends on the application, right? For example, here, looking at this picture, this is a PIC of, let's say, 5 by 5 millimeter, more or less. And this one houses, in this case, something like 8 or 10 tunable lasers. So you probably could have doubled that, something like that. So, we're talking about a few millimeter square photonic ICs. In terms of the 3.5 device size, as you can see here, actually, if you look at this PIC, only a very small fraction of the area of the PIC is actually 3.5. So this is another advantage of microtransfer printing, is that you only put the 3.5 where you need it.
Exactly.
Compared to die-to-wafer bonding, you would put a bigger die here, and then you would etch it away everywhere where you don't need it. So it's a less efficient way of using 3.5 material compared to microtransfer printing.
In short, Pratyusha, I think electronic devices are much smaller compared to optical devices. So maybe we can talk offline if you're a student.
Yeah, so maybe just another data point I could bring is, so for example, in this Caladan project, I didn't have a slide on it, but we are also transfer printing electronic drivers and receivers. These chiplets, they are about 300 by 200 micron. So you have a transimpedance amplifier then, and a driver is slightly larger, I think, but okay, it's a few hundred micron by few hundred micron compared to the few millimeter by few millimeter from photonics.
Right. But yeah, I mean, that IC in itself contains several devices. So
sure.
Yeah. The next question is from Pavan Kumar. What is the typical loss for evanescent coupling, and how carrier distributions of active devices affect the coupling?
Yeah, so that's a good question. So actually, it's not so easy to measure as well. Let me show the picture. Where is it? Yeah, this one, for example. So as you can see here, indeed, we are so our taper structure, we are reducing the width of the 3.5. But in our classical devices, this 3.5 here is also active, meaning it has also the quantum well active region here, which means that the efficiency of the coupling also depends strongly on how efficiently you can pump this this waveguide structure. So if you were to be able to perfectly pump it, then you can get close to 100% coupling, as you can see from these simulations. So it's much less than half a dB of coupling loss between the two. But the question is, how efficient is this pumping here? That's why in our new projects, the Inspire project, try to find back the slides. Yeah, here. We are actually going to use active-passive integration. So we are going to have a regrowth step in the 3.5, and then butt couple the active region with a passive taper structure. So in that way, we should be able to really come close to this sub half a dB of coupling efficiency between the 3.5 and the silicon or silicon nitride.
Very impressive. Yeah, I just wanted to add, I mean, it's also a tricky thing to measure, right? So
yeah. So that's why I don't want to give a number
right
now, because it's, as you say, it's hard to measure. But I do believe that if you make use of this active-passive integration, you can come very close to the theoretical sub half a dB coupling efficiency.
Right. I think this is the last question from Yesh again. Is there no lattice mismatch related issues when we simply place our device on the wafer?
No. So this is a bonding approach. So there is no, there is no need for matching the crystal lattice between the source and the target. There is either there is an adhesive layer that takes care of the bonding, or can also even do molecular bonding. So no, that's not really a problem. It's actually the beauty of these bonding approaches, right, compared to heterocontextual growth, is that you don't have to worry about lattice mismatch.
Yep. precisely. I think there's just a question popped up last minute. Anushka asks, what are those BCB layer on which doping is done? I don't think I understand the question myself. Anushka, do you want to maybe just unmute yourself if you're online and if you can talk? What do you mean by doping in BCB? There's no doping in BCB.
I think
Okay.
we need to unmute, otherwise
Hello.
they cannot unmute themselves. Yeah.
So perhaps I could just say that the BCB is just used as an adhesive. So we spray coat that BCB here, a very thin layer, a few tens of nanometers of BCB, and then we print the 3.5 device in that cavity and cure the BCB.
Right.
That's
I think
the only
Anushka is
function.
online. Can you speak, Anushka?
Yeah, last night which was there earlier, there DBRs were there. So the doping was done
On the VCSELs.
For the VCSEL, yeah?
Yes. So
Yes.
these dopings are done on.
No.
Sorry, you disconnected. I'm assuming she's asking how the DBRs are doped PNN, but I'm assuming that's coming from the 3.5 wafer, from the epitaxial
Yeah.
wafer.
This is classical 3.5
Yeah.
stuff. So it's
So there's
just
no doping done after
during
bonding.
the growth. Yeah.
Right.
Yeah.
Right. I think that is all the questions. I can probably ask the couple that I had. So you showed us like two epi stacks being transfer printed. Were they from two separate wafers, or did you use some kind of selective area growth on the same wafer?
No, they're from two separate wafers.
Okay.
Yeah, so they're not printed together, but they are printed sequentially.
Got it. And maybe I missed this point. Like, how did you manage to make the VCSEL single mode? Is it from the aperture that you show, the oxide aperture?
It's actually a combination of indeed the aperture, which is, if I remember well, 4 micron.
Okay.
But we also saw that by putting the grating below, we could actually go larger in aperture diameter and still get single mode operation. So there's also some mode selective feedback from the grating. So it's a combination of the two.
That's very interesting, actually. So I think that could be a powerful tool. And another thing, I just wanted to maybe understand the tool a little bit. So how does it register that it's made contact to the wafer? Is it like a pressure sensor, or given that it's compliant, I was just curious, how is the Z calibration done? And
well, you do that up front once for your wafer assembly on the chuck, and then it just there is no real in situ control over the amount of overdrive you have, but it just relies on the heights you calibrate it, and then
okay, so some kind of independent laser measurement that tells you where you are in Z, and you sort of calibrate all your tools with respect.
Well, I think it depends on. I mean, at the moment we are still doing most of our work on a lab scale tool. So there it's a little bit more manual still at the moment, this calibration. But our plan is indeed to move to an industrial tool like this one. And there indeed there are these height sensors incorporated, but I don't know, to be honest, the details of how they work.
And maybe my final question is, I was really intrigued by the concept of getting electronic chips onto silicon PICS. The goal there is to have them so that they're all planar, and then you do a single RDL metallization after
Yes.
that to connect between. Okay.
Yes, indeed.
Do you usually
for
have
example,
to worry about like different heights and things like that, like thicknesses of chips?
That's a very good point. So okay, a typical 3.5 component would be something like 3 micron thick or so. The electronic chiplets that we are transfer printing here, they will rather be 15 micron thick. So there is indeed a height difference, but this is not something. I mean, this is not impossible to overcome with an RDL process. So the idea is still that with a single RDL, we can connect the 3.5 devices either to the silicon photonics backend or to the pads of the electronic chiplet.
Very cool. I'm really looking forward to some of those results in the future. And yeah, I think that's all the Q&A questions I see. So I'll probably hand it over back to Bijoy, and we can probably conclude this session.
Sudarshan, I have a couple of questions I thought of.
Oh, sure. Oh, sorry. I'm so sorry. Yeah, go ahead, Bijoy.
Gunter, it's a very excellent talk. I think a lot of information. We learned a lot. So, thing is that what is the yield of this type of laser when you integrate? So, kind of we were talking about MPW runs, all those type of things. What is the yield? Is it 90%?
Well, so as I said, at the moment we are still mostly working with a lab scale tool, so it's hard to, from what we do in the lab to say something sensible about yield. Although in other projects we are starting to use these wafer scale tools. So there, the first results look actually very good. So we have over 99.5% of printing yield. So that means the yield of releasing components, picking them up, and printing them. We still now have to take the next step and see how the laser characteristics are spread out. So that number we don't have yet, but the actual printing process itself can be very high yield, and it's not really limited by the printing. It's limited, in our case at least, by the 3.5 source wafer preparation. So you can already see on the source wafer if a coupon will print well or not print well. So if we have to work further on improving the yield, it would be on improving the source wafer. That's also the reason why we work together with these 3.5 foundries, because of course they have better controlled 3.5 processes than we do in our university clean room.
Yeah, I have a curious question. Normally always we complain that okay, silicon is bad for laser integration, and you come out with a solution that's very good. But when we use off-chip laser, we have so much packaging control, temperature control, etc. is there. When you just mount on the photonic chip, silicon chip, as you increase your driving current, any laser cavity wavelength shifts.
Mm-hmm.
So you need a good temperature control also. So you need also on chip locally temperature control, that type of packaging, meaning bonding required. So also you are working in that direction also, because different application we need different characteristics. For example, you are developing mode lock laser also 1 gigahertz refresh rate.
Yeah.
And I go for
well, I would say, I mean, I'm not suggesting here that heterogeneous integration or by whatever means is always the best solution, right? Indeed, if you need a very stable laser source that has to interconnect with a photonic IC that operates in a very harsh environment, then I would not recommend heterogeneous integration. Then an off-chip laser is indeed the best approach. However, there are other applications where you can live with the typical thermal effects that happen to a laser or an amplifier. So you're right. You have to make a judicious choice whether for your application integration is the way to go. You of course you gain a bit in terms of compactness and costs. But on the other hand, if this compromises the performance of the laser, then it's not the way to go.
But I think that there may be a possible solution. Maybe you are also looking forward ahead, I guess, on chip probably. Those type of temperature control and all those type of things. Is it possible? My question is that how much realistic in future also, if not today?
Yeah, temperature control on the chip. I mean, it's not so difficult to put, let's say, a heater next to the laser, but then you always have to operate it at the highest possible temperature. It's much more difficult to get micro thermoelectric coolers on the chip. So this is not something we are looking into at the moment.
Maybe you could transfer print a TEC on there.
Yeah.
Maybe, yes, maybe.
Yeah, I do remember a very old publication that talked about having microtex next to the laser mesa.
Measured structure.
Just to cool the laser mesa.
Yeah, would be an interesting research topic. Yeah.
Yeah. Okay. That's all from my side.
But,
I think,
but for example, this case here, exactly this project, the gallium arsenide quantum dot lasers, we use these materials because they are supposed to be temperature insensitive. So at least to some degree. So you can also choose the materials right to not having to cool the component.
Okay. So is this technology IMEC is also adapting this thing, or?
You mean the microtransfer printing?
Well,
at IMEC we are exploring all possible options. Which one will survive in the end? Only the future will tell. But yeah, we're definitely taking this one seriously. Yes.
Okay. That's good.
So actually, currently we are doing a first kind of MPW run for this kind of technology. So where you can design.
Yeah, that is what I saw the announcement.
Yeah. So where you can design a classical IC50G chip. And then we can transfer print on a die level at the moment. We can transfer print SOAs on that chip. It's not yet as mature as the the IC50G, but we're taking first steps.
Yeah. Okay, Sudarshan, I'm done.
Yeah. No, thanks, Gunter. That was a very great talk, and thanks for engaging us and taking up all the questions patiently
Thanks
from
for the
everyone.
invitation.
So yeah, I'll probably hand it over to Deepthashree now, or if you want to say some concluding remarks. And thanks all for attending, and thanks once again, Gunter.
Thank you, Professor Gunther, for this wonderful presentation. And also thank you, Professor Sudarshanan, for handling our Q&A session very nicely. And my heartful thanks to all the participants. I'm sure you have enjoyed the entire session. And our next webinar talk will be delivered by Professor Silverhorn from Paderborn University, Germany. So hope to see you all again. Have a nice evening.
Okay, thank you.
Thank you, Gunter. Thank you.
Bye-bye.
Bye-bye.
Bye-bye. See you guys.